Hello everyone, welcome to Pen and Paper. Actually today we are going to discuss the most important property of parabola, which is unfortunately not present in any of the JEE books, and it is very important, so I felt the need of discussing this with you guys. So let's get started. Suppose we are having a parabola this way. Okay, first I will mention the property and then I will give its detailed proof. In general, we know that from any point inside the parabola, we can draw three normals because we have the equation of normal as y equals to mx minus 2am minus am cube. So this is a cubic. So we can say that in general, we can draw three different normals from a point inside the parabola. And let's say we have a point inside the parabola as P, H, comma, K. So if I'm drawing if I'm drawing normals from this point, this is the equation of normal. So I can say that this point is going to lie on this curve. That means on this straight line. So if I put H, comma, K in this line, so I will get ultimately AM cube minus H minus 2A M plus K equals to 0. But it is very important to know that we cannot draw three different normals from each and every point inside the parabola. I am saying that, let me draw a curve this way. So according to this property, I am saying that if this is my region A, this shaded part, if I am saying if this is my region A, okay, and this curve, this curve, this curve is my region B, and this vertically shaded region extended up till infinity is my region C. Okay, so all I am stating is that in region A, I can draw from any point inside the region A, I can draw only one normal. And for any point on this curve B, that means let me shade it with some other color so that it is more clear. This is purple, okay? So this curve, which I have shaded in purple, this curve, for any point on this curve, we can draw two different normals. And for any point beyond this curve, that means any point beyond this curve extended till infinity, that means in region C, we can draw three distinct normals. So let's suppose if you are given some point in this region, so you can directly state that in this region, from this any point in this region, I can draw only one normal to this curve. But now, what is the equation of this curve shaded in purple? This would be 27ay square equals to 4x minus 2a whole cube. Okay, let me put this inside the box. Fine. Now, this point of intersection, this point, this I will call as cusp, and my this point, let me say this is my point. This point would be 2a comma 0, this point, and this point where this curve intersects the parabola, these 2 points, let me call this point as point Q and this point as point R. So point Q would be 8a comma 4 root 2a, and similarly point R, for point R it would be 8a, and y coordinate it would be negative, so minus 4 root 2a. Now at this point where this purple curve intersects the parabola, from that point we can draw only one normal. So at all the points on this curve we can draw two different normals. From this we can draw two different normals to this parabola, except at this point where it cuts the axis, which is 2a comma 0, and where it cuts the parabola at points Q and R, except at these 2 points, because at Q, R and at this point we can draw only one normal. Now there is one more thing. Now I am stating that all the normals to this parabola are going to be tangent to this curve, this curve, this curve, and I will prove this. Now one might say that, like suppose if I'm drawing one of the normals, let's say I'm drawing it with blue. Let's say if I'm drawing one of the normals this way, one might say that for this branch of this curve, this is not tangent, but it is going to be the tangent for the other branch of this curve. So here we are having two different branch of this curve. So this normal to this parabola is going to be tangent to one of the branches of this curve. And we are going to prove this as well. And we are going to prove each of these things in detail right now, that why only one normal can be drawn in this region A, why two normals can be drawn from the curve B, and why three normals can be drawn for the region beyond this curve. So this is a cubic in M. So all I'll do is I'll assume a function g of M as AMQ minus H minus 2A M plus K equals to 0. Now let's talk about the case where two normals can be drawn. Okay, if two normals can be drawn, that means two different values of slopes are possible, that let's say M1 and M2. So two roots are possible. So can I say that the third root would be a imaginary root Z? No, certainly no, because the complex roots always exist in pairs if the coefficients are real, and obviously in this cubic all the coefficients are real. So this is not a possibility. So the only possibility is left is that we can have two coincident roots, M1 M2, M1 M1, and the other one as M2. Okay, that means let's move it downwards. That means These are the only possibilities, two coincident roots and the other one different. So basically we are getting two different roots, m1, m2. Now if we take the sum of the roots, I will get 2m1 plus m2 equals to, the sum of the roots is going to be 0 because the coefficient of m square is 0. Now if I take the product of the roots 2 at a time, so I will get m1 square plus 2m1 m2 is equals to h minus 2a, or minus h minus 2a by coefficient of m cube, that is a. Fine. Now if I take the product of the roots, I will get m1 square m2 is equals to minus k by a. Fine. So from here I am getting m2 to be equal to minus 2 m1, m2 to be equal to minus 2 m1. So I will substitute m2 equals to minus 2 m1 over here. So I will get m1 cube equals to k by 2a. All I have done, I have substituted m2 equals to minus 2 m1 in this equation. Okay. So from here I am getting m1 to be equal to k by 2a to the power 1 by 3. Fine. K by 2a to the power 1 by 3. And now I will substitute this value of m1 in this value of m1 in this equation. So m1 square would be k by 2a to the power 2 by 3 plus 2 m1 m2 plus 2 m1 m2. Fine. So m2 is equals to minus 2 m1. So 2 m1 m2 is going to be 2 m1 m2. If I multiply here 2 m1, so this would become minus 4 m1 square. Okay, minus 4 m1 square. So this quantity 2 m1 m2 is going to become minus 4 m1 square. So minus 4 m1 square, that means square of this quantity, that means k by 2a to the power 2 by 3, and this is equals to minus of h minus 2a by a minus of h minus 2a by a. Fine. Now this quantity is minus 3 k by 2a to the power 2 by 3. So this minus and this minus will get cancelled. So I can write plus 3 is equals to h minus 2a by a. Now if I cube both side, and if I replace h with x and k with y, because this is what we do in finding the locus. So if I cube this, I will get 27. Here this k would become y square. Okay, and here we are going to get this a this side, and here on cubing this will become x minus 2a whole cube, and this 2 square 4, so 4 will come over here, this a square a cube and this a square, so finally we are getting a over here. So this is my curve which I have already shown that this is the curve from which we can draw two different normals over here. If you look over here, this was the curve shaded in purple, and the equation was this, which we have proved over here, that how we are getting this curve. And this was a case where we have taken for two different normals. Okay, now let's talk about a case where we can have three different normals. So if I'm talking about a case where I'm having three different normals, that means, okay, let me write this function again so that I don't have to scroll back. Okay, so my GM was a m cube minus h minus 2a m plus k equals to 0. Now if I'm talking about three different normals, that means obviously I'm talking about the real normals. So we are going to have three distinct normals. That means we are going to have three distinct roots of this cubic. Let's say m1, m2 and m3. We are going to have three distinct roots. So if we are having a cubic, if I'm having a cubic and it is having three distinct roots, that means the cubic is going to cut the axis at three different points. Let's say we have this as x-axis, so it is going to cut the curve at three different points, and let's say this point, the x coordinate of this point alpha is where the local maxima is attained, and the x coordinate of this point is beta, this is beta, where the local minima is attained. Or we can have a case that the graph of this cubic is this way. That means here at alpha we are having a local minima, and at beta we are having a local maxima. So we can clearly see that g dash, in either of the cases, g dash alpha is equals to g dash beta, and that is equals to 0, because local maxima minima is attained. That means g dash alpha, g dash beta is going to be 0. Now if you look at this graph carefully, we can state that g of alpha into g of beta is going to be less than 0. Why? Because in this case g of alpha is positive, in this case g of beta is negative, so their product, positive into negative, is turning out to be negative. In this case g of alpha is negative and g of beta is positive, so negative into positive is again turning out to be less than 0. So if g of alpha into g of beta is going to be less than 0, that means let's say this is my g of alpha. What is my g of alpha is going to be? G of alpha. That means, but before getting g of alpha, let's find out alpha. We are having g dash alpha is 0. That means g dash of m is going to be 3a m square minus h minus 2a Now to get g dash alpha, g dash beta equals to 0, I need to equate this with 0. So from here I am going to get the value of alpha as root under h minus 2a by 3a, and the value of beta is going to be negative of this, so beta would be minus alpha. So g of alpha into g of beta is less than 0. So ultimately g of alpha into, instead of beta I will write minus alpha. G of minus alpha is going to be less than 0. Fine. Now g of alpha, what I'll do, I'll put g of alpha, so instead of m I'm going to put alpha, so I will take alpha common. So this here it should be alpha cube, so it would be only alpha square. Fine. And here it should be alpha, but since I have taken alpha common, here I would be left with only h minus 2a, and obviously plus k over here. Okay. Now my g of minus alpha. Actually, one more thing that I need to explain is that here we are going to get two different values of alpha. One is h minus 2a by 3a root under, and the other would be negative of this. So obviously, which that I have assumed as beta, so beta is negative of alpha. Now g of minus alpha is going to be minus alpha a alpha square minus h minus 2a plus k. So g of alpha into g of minus alpha is going to be, this is in the form of a plus b into a minus b. So k square minus, like we do in a plus b into a minus b as a square minus b square. So k square minus this whole quantity square. So that would be alpha square into a alpha square minus h minus 2a square, and this would be less than 0. Now my alpha was this, so my a alpha square, my a alpha square is going to be h minus 2a by 3, h minus 2a by 3. So instead of a alpha square, I'm going to write here, I'm going to write over here h minus 2a by 3, and here we are having h minus 2a and alpha square, so this would be h minus 2a by 3, and here k square, this is less than 0. So this would turn out to be k square minus, this is h minus 2a. So this quantity inside the bracket is minus 2 by 3 h minus 2a. So square of this, okay. So h minus 2a, here we are having square actually. So h minus 2a square into h minus 2a. We are going to get h minus 2a square into h minus 2a, so cube. Fine. Now here it should be actually a. So square of 3 is 9. 9 into 3a is 27a, and square of minus 2 is 4. and this is less than 0. So basically we are getting, if I replace k with y and h with x, so I will get y square. In fact, on taking LCM, 27 ay square minus 4 x minus 2a whole cube less than 0. And if we look at this curve, this was same as this curve, and remember, whenever we have any curve, let's say we have any curve this way, okay, if we are having any curve this way, so if we are having any point over here and any point over here, that means these 2 points are lying on either side of this curve. That means if we put this point in this curve and this point on this curve, we are going to get 2 different signs. So if this is my curve S, let's say S1, okay, so let me put origin over here. Let me put the point O 0, 0 in this curve. So if I put 0, 0 in this curve S1, I am going to get S1 to be 8a cube, that would be positive. And now if I put any point for which S1 is turning out to be negative, can I state that these 2 points are lying on either side of the curve? So if you look at this graph, over here, this graph, origin is lying over here, okay, origin is lying over here, and for any point lying over here on this side of the curve, these two points are going to get 2 different signs for this branch of the curve. For origin, we already showed that this S1 turned out to be positive. And for the case of having 3 distinct normals, I showed that S1 is less than 0. That means one is positive, one is negative. So origin is this side. That means those points for which we are getting negative should lie over here, over here, over here, over here, over here. That means on the vertically shaded region, because vertically shaded region and origin, they are lying on 2 different side of the curves. And as I mentioned over here, that for any curve, and we are having 2 points lying on either side of the curve, so we are going to get 2 different values of the curve. One would be positive and the other would be negative, or one would be negative and the other would be positive. That means they are going to have different signs. So now we have already proved that beyond this curve we are going to get 3 different normals. So we already covered the case from where we can draw 3 normals. We already covered the case from where we can draw 2 normals. Now if I'm talking about the case from where 1 normal can be drawn, that means all the region except region from where 3 normals can be drawn and 2 normals can be drawn. So the left out region, that would be the left out region. So the left out region would be the region from where we can draw 1 normal So the left out region is this region, which I have mentioned as region A, which has been shaded in horizontal black lines. This is the region from where we can draw one normal. That means we can specify something more. If we can draw one normal, can I state that this cubic, that means this function, is going to have one real root, let's say m1, and two imaginary roots z1 and z1 conjugate, because we know that imaginary roots exist in pairs if the coefficients are real, and obviously the coefficients are real. We could have had the case where all the roots were coincident, but I am stating that we are going to have this case and not this case. Why? Because if all the roots are coincident, can I say that this gm would then become in the form of a into m minus, let's say, some constant c cube? Can I say that when I expand this, I'm going to get some coefficient of m square? I'm going to get some coefficient of m square, This is not going to be 0, but here the coefficient of m square is 0. That means this case has been ruled out. So we have only one possibility, that this cubic is going to have one real root and two imaginary roots. So you can specify, it can be asked that for any point, let's say we can have a point in this region as, let's say, 3a comma 2a. In this region we can have a point 3a comma 2a. So for this point in this region 3a comma 2a, let me call this point as point q, this point q 3a comma 2a. It can be asked that for this point, what are the nature of the roots of this cubic? So you can specify that one of the roots is going to be real and the other two roots are going to be imaginary, and the number of normals that can be drawn, so you can state one normal can be drawn. Now, while stating all the properties, I also mentioned that the normal to this parabola is going to be tangent to one of the branches of this curve, right? So I need to prove that as well. Fine. So if this is my curve, so parametrically what I'll do, I'll assume I'll take x minus 2a to be equal to 3a 3a t square, and y to be equal to 2a t cube. So if you put this point over here, you can clearly check that this is going to satisfy this curve. So parametrically I have taken it in this way. So from here I am going to get x is equals to 3at square plus 2a, and y is equals to 2at cube. So to get dy by dx, I can write dy by dx as dy by dt by dx by dt. That would be 6a 6at by 6a, actually it should be 6at square, dy by dt 6at square, and dx by dt is going to be 6at. So finally we are going to get t. And let's say we have some point, we have some point on the parabola as a t1 square comma 2a t1 for the parabola with equation y square equals to 4ax. Now I know that my dy by dx from here would turn out to be, in a similar way, dy by dx would turn out to be equal to t1. So for t equals to t1, obviously the solution exists. We can always find a t for which t is equals to t1. So for this solution, we can say that the normal, that means this normal is actually tangent to the curve because their slopes are same for this value of t, for t equal to t1. And now one more question that must arise in your mind is that I have drawn this curve. This way, right? Why haven't I drawn it this way? Why I have drawn it this way? So if you differentiate this curve, you will get y dash. You can easily check that for y greater than 0, y dash would be positive. Now, y dash positive means the curve is increasing. For y greater than 0, curve is increasing. That means the curve can increase either this way or this way. But why I have drawn this way? So to get to know this, we need to differentiate the curve again. And if you differentiate this curve twice, so you are going to get y dash also greater than 0 for all y greater than 0. So if y dash is greater than 0, that means the curve has to be concave upwards. Now what about this branch of the curve? So we don't need to worry about this branch of the curve. The reason being, if you replace y with minus y in this curve, the graph remains, the function, this curve remains unchanged. So if we are replacing y with minus y and this curve remains unchanged, all it means that the curve would be symmetric about x-axis. That is why the curve is this way. And now, as I have mentioned the point Q and R, it might be asked to you that what is the area of the region within the parabola from where you can draw one normal. So the area would be this horizontally shaded region. And what would be its area? So its area is going to be, let me write it over here. Integration from 0 to 8a. Why I have written 8a, I will explain everything, don't worry. 8a y square, where y square is equals to 4ax. So we are going to take only the positive value, y equals to 2 root a root x. Okay, for y we are going to take this value, and why we are taking only positive value, that also I will explain. This minus 2a to 8a y1 dx, where what is my y1? Here I am stating 27a y1 square equals to 4 x1 minus 2a whole cube. The reason why I have written y1 over here, to differentiate this y with this y. Okay, so for this y1 also we are going to take only the positive value. Only whatever value we are going to get, we are going to take only the positive value and not the negative value. And to this we are going to multiply with 2. Reason being, why I have done this. If I scroll back, I integrated the curve from 0 to this parabola. Integrated from 0 to this point. This point is 8a. So let me shade this with yellow, purple, or yellow. So I got, when I integrated from 0 to 8a, I got this region from here till here. Okay, till here. But I wanted only till here. So what I did, I integrated this curve, this purple curve, from 2a to 8a, because the x coordinate of this point is 8a, and I subtracted this area. So I got, when I subtracted this area, I got this area, but I need to take double of this because I need to consider this area as well. That is why I have subtracted this from this curve 2a to 8a, and I have taken twice of this. So this was the very important property. Hope you liked it, and make sure that you like, subscribe, and comment on this video that how was this video. Thank you.